So good afternoon, everyone. Welcome. I see Zurab is already setting up. Welcome to this third lecture. No, Zurab, please go ahead. This third lecture of the introduction to set theory by Zurab Janelidze and Amartya Goswami. We introduced you to the speakers already twice, so there is no more need to introduce them today. You all know them very well by now. And I see Zurab is already very anxious to start. So Zurab, please share the screen so that you can start. And I leave it to you. And the participants by now know the rules of the game. Just raise your hand and we can give you the right to speak, or just post it in the Q&A. And Zurab and Amartya are very expert Zoomers, so they always keep an eye on the chat and the Q&A, and I will assist if need be. So please, Amartya and Zurab, over to you. We are all curious to see part 3 of the set theory story.
Thank you, Francesco. So Zurab, we talked about sets. We also give some examples and describe some structures, mathematical structures. Maybe we construct new structures from given mathematical structures. We discussed a little bit about that. Maybe integers could be a simple choice. We already mentioned about that integers are groups, if I remember, in our last lecture. So what do you think?
Yes, so somehow last time we began with something that was like a notion of vector space, and we described how to encode it in the language of sets. But the tools that we discussed that allow us to achieve such encoding were not exhaustive. There are more tools, and in fact, one of the fundamental tools in set theory for expressing various constructions is the notion of partition of a set.
Yes.
And that links with what you said, but we would actually need partition to maybe create rational numbers out of
yes, from integers.
But let us, is it okay if we first maybe describe the general concept before we look at the application?
Yeah.
So using the kind of pictures we've got used to by now, if we have a set, let's say X, so its elements are displayed in this bag that kind of expands X. Then we might want to group elements of X by type.
Right.
And that idea of type can be really anything. It can be a very abstract idea as well. But eventually it results in dividing the set up into portions like this. But then we want to form a new set, which is the set of these groupings themselves. So this set will be one element of that new set, and this will be another element. Oops, I missed one there, sorry.
Yeah.
So this will be another element. Then we have the third one here, and the fourth one.
So basically from this picture, if X is the original set, we constructed a new set with 4 elements.
Yes, and this new set deserves a name also. We can call this set, we can call it P.
Right.
So the set P is called the partition of the set X.
But are you going to impose some conditions how we do this division of the set itself? Like, should we include a specific element of the original set? Can it be in 2 different bags or smaller bags, or it should be in unique bags, right?
Yeah, so the rule is something that is kind of suggested by the picture. Empty groupings are not allowed.
Yes.
And groupings cannot overlap. You cannot have, for example, that you group things like this, where this element belongs to two groups, this one and that one.
Mm-hmm. That one.
Something like that is not allowed. So, but I think the picture is suggestive of the general concept of partition. And so basically we create a new set out of X, right? So the set X gives rise to the set P. And coming back to now your question of how we could, well, first of all, let's discuss how we can build integers out of natural numbers. That is going to be maybe a little bit boring, maybe not. So by the set of natural numbers, we have, what we have in mind is the set 0, 1, 2, and so on. And one way of encoding these as sets is, as we discussed earlier, to define 0 to be the empty set. And then every n will be defined in terms of the previous numbers that have already been defined. So it's a recursive definition. Yes. So n can be defined as the set of numbers from 0 from to 1 to 1. From 1 to n.
Yeah. Right.
Sorry, n minus 1. Okay, so now once we have constructed the set of natural numbers, then we can create the set of integers by choosing two symbols. One will represent plus and the other will represent minus, and this could be some two randomly chosen sets. For example, plus could be the empty set, and minus could be the set whose only element is the empty set, which, by the way, according to our definition, is actually number 1. But we don't have to think of that number 1 right now. I mean, we don't have to think of that as number 1. And then we take the Cartesian product of n, but we actually want to consider n without 0 for now. So we remove 0. This is one way of, this is the way of removing elements from a set. So this operation a minus b, called the difference of sets, it's defined the following way. You put in this set all the elements of A that are not elements of B.
Of the B.
So if I have a picture for it, if A is such a set, and B is a set of this kind, then A minus B will be that set. So this is A minus B. So it simply removes all the elements of B from the set A. So we remove from natural numbers the number 0, and then we take the Cartesian product of that with the symbol plus. So this is how we can think of positive integers. So Cartesian product with a set whose element is plus.
So it's a singleton set.
Yes. So the elements of this set will be ordered pairs plus n, where n is a natural number and n isn't equal to 0.
0.
And then we take the union of this set. The union means just put elements together. The union of this set with 0. And then we take further union with negative integers, and that will be the symbol minus, the singleton set of symbol minus, and take Cartesian product of that with the same n
non-zero integers. Yeah, sorry, non-zero natural numbers. Yes.
So this will be the set of order pairs minus n, where n is in n and n is in 0. Now I can think of this expression, the order pair plus n, as plus n. I mean, I can symbolically use this notation to represent that ordered pair. And similarly, I can use this notation to represent the other ordered pair. So we would have then built something that we can call Z. So we can think of this as the definition of Z. So this would be one way of getting to a set that contains integers. Okay, but now the next question is how to move from Z to the rational numbers. And again, we can use the idea of ordered pair. We could take Z cross Z. So consider pairs of integers. But of course, if we do that, then we get too many numbers, right? So because I mean, the idea here was to think of this as the fraction n over m.
And so also there is a problem that whether we take 4 pair and 2 pair, we do not want them to be different.
Then we have too many, because 1 over 1, we want this to be the same number as, let's say, 2 over 2.
Yeah.
But being defined as pairs, the pair 1, 1 is not the same as the pair 2, 2, because pairs being same means that components are equal. So what we have to do is we have to collect all the set of all such ordered pairs and group them together, like we did in the very first picture, where in each grouping we will contain those pairs which represent the same fraction. Of course, there will be infinitely many. Yes, there will be infinitely many such groupings. So then the pair 1, 1 will go in the same group as the pair 2, 2, and also as the same as pair minus 1, minus 1. Of course, by 1 now we mean plus 1. So maybe I should be a bit more careful here, the way we defined in a technical manner. So we will put, I mean, in general, when will n over m represent the same fraction as k over L?
One thing probably we need to be a little bit careful about the pair 0, 0.
Actually, you're right. We don't want to have 0 in the denominator. Yeah. So, in fact, what we really want to do is to exclude that possibility, and we can do this because the denominator was the second component of the ordered pair.
Right.
And we could remove possibility for the 0 to be second component by removing 0 from the second set in the Cartesian product. Or we could have removed those pairs later.
Zeros, and add it up. Yeah.
Again, using a subtraction of sets, the difference of sets. So when m and L are, but now m and L cannot be 0 anymore after this adjustment, and where they're not 0, these pairs will be equal if and only if n times L equals m times k. Of course, this does mean that we have to first define multiplication and so on, but let's assume that we've already done that. If we can multiply integers, then we can use multiplication of integers to describe how we form this grouping. So basically, we say that we will put n m ordered pair in the same grouping as KL ordered pair when
this identity will be satisfied. Yeah.
And then we do still have to ensure that these groupings do not overlap, that we don't have empty grouping and all these things. That's not difficult to check that. It's just a simple arithmetic manipulations. And now we take this partition. So the new elements of the new set we obtain is the set whose elements, each of them, are groups. And this new set, which is the partition of the previous set, using the grouping that was described just now. So this was our previous set. This new set is the thing that we can call the set of rational numbers.
Rational numbers.
So this way we build rational numbers out of integers. Now, there is important philosophical point to be made here, namely that we view a number, let's say 1/2, as a set of all possible fractions that basically satisfy the following, right? So it's a set of all, if I think of 1 and 2 being my n and m, right? So this is all possible pairs KL such that
identity.
Yes, so such that L equals 2K, right?
Yes.
So if I put here 1 and there 2, I get L equals 2K. So this is important thing to understand because even at school, when they explain what a fraction is, right, they don't make it very clear, this point. So when we say that 1/2 is the same fraction as 2/4, for example, what does it mean that it's the same fraction? We first have to define a fraction before we can say that they're the same. And so set theory allows you to define a fraction as a set, and then this set 1/2 and this set 2/4, which will then be, by the same definition, the set of all KLs, such that, so this time we are putting 2 and 4 here, such that 2L equals 4K. So the fractions now being the same means that the sets are the same. But of course, sets are the same means that they have the same elements.
Yes.
And of course,
this reminds me about this high school type of definition of rational number. You have P/Q, where Q is not equal to 0, and it is in the lowest form. And that lowest form is not very precise until we see it more proper way in this set theoretic way, because lowest form in the sense that they all belong to the same bag.
And so just confirming that this bag, as you say, is the same as that, is just confirming that these conditions are equivalent. And of course they are, because you multiply, divide by 2 to get one from the other.
Right.
But this philosophy of defining objects as sets arising in a partition can be used already for extracting the idea of a natural number from real life. And I want to maybe give that example as well. So in the same way, we can, instead of defining, like here, we defined in the beginning, we defined natural numbers as specific sets, right? Just like you said that the way the fraction problem is maybe avoided sometimes at school is to divide fraction, define it in the lowest form. So you define it as a specific ordered pair. So you define, so this is a fraction then in that definition, but this one isn't. I mean, this is a rational number, but this one isn't, according to, so because you pick one specific. In the same way here, we are forcing n to be one specific set having n elements, right? But we could also use a different approach where we put in one large bag all possible sets that we encounter in real life. So for example, one element of this would be the set of 2 apples. One apple and the second apple. Another element could be the set of an apple and a pen. Okay, a set of 2 things, and so on. So we any kind of sets of objects we can find in real life, we can put them as points in this bag. So the points in this bag themselves are already sets of objects in real life. And then we group these things. We form a partition where two sets of objects will belong to the same group when the amount of elements inside them is the same. Like, for example, this one and that one, they both have two objects in the set. So we group them together, we put them in the same group. And there would
basically,
yeah,
we can do this kind of partition of any sets as long as we follow the same rule for each of these division. Then we can always construct such a partition.
I mean, we're not talking about division anymore. We are talking about
no, not division in that sense. We divide the whole set into smaller pieces, and that process we can do as long as we follow the same rule for each of these pieces.
Yeah, so in our case, the rule is that two different sets of objects will go in the same grouping when the amount is the same in those sets. It means there is one-to-one correspondence. The amount being same, by the way, doesn't mean we have to count them. Again, the amount being same can be defined set theoretic way, that's like we discussed last time, by saying that there is a bijection, one-to-one correspondence between those sets. And then we will have one grouping which represents empty box, a box with no contents, and this will be one grouping. Then another one which represents sets having one object in it, then another one sets having two objects in it, 3 and 4 and so on. And this new set we form can be seen as the set of natural numbers. So with this approach, we define, let's say, number 5 to be the set of all sets of objects having 5 objects in it. So a number becomes a set, and this idea that a number becomes a set of all the examples of that number. I mean, in a sense, what we're saying here actually is that number 5 is a set whose elements are all examples of 5, because when we explain numbers at the very beginning of our youth, when we understand numbers, we think of examples of numbers as, like for number 5, we think of the example being 5 apples or 5 pieces of tomato and so on. And so number 5 becomes the set of all of its examples.
So it doesn't matter which object we actually pick it up to represent this number 5, whether it's a 5 apples or 5 pens or 5 books, doesn't matter. That's the whole idea here we are trying to convey. So
the set we started with, right? We can think of this as the set of concrete numbers. In other words, numbers that are given some interpretation, as number 5 given interpretation as 5 watermelons, for example. And the partition allows us to get a set which will be whose elements will be abstract things. So it will be the set of abstract numbers. And this links to another application of the idea of partition, that partition actually can be seen as a set theoretic way of understanding abstraction.
So it is very funny, Zurab, that to a mathematician, 5 watermelon is same thing as 5 fountain pen.
Yeah. That's the story of applying partitions in building number systems and other things like that. But there is also a very impressive application of partitions in building spaces. For example, if we begin now, we didn't discuss how to create real numbers out of rational numbers still, if we skip that part and let's say we already created real numbers, we already know what the unit interval is. So we think of this as a subset of the set of real numbers. Then out of unit interval, we could define.
Maybe we just to mention a little bit, if somebody is not quite familiar with this square bracket notation, what do we mean actually, which real numbers?
Yes, I will write this out, and meanwhile, maybe we could ask Charles to ask his question or make a comment because he has a raised hand.
Charles, please go ahead.
Sorry, Francesco, is it possible for a participant to ask questions?
Yeah, I can. Sorry. I can give. Voila, here. Sorry.
Thank you.
Charles, your microphone is muted. Now it's fine.
Can you hear me now?
Yes.
Yes.
Okay. Can you please go back to this partition we are doing? Yeah. That's two, where you've got two apples, and then somewhere you've got an apple and a pen, I think. Is it an apple and a pen?
Yeah,
yes.
Yeah.
I'm a bit uncomfortable there. What do you call that? Is it a set of a pen? Are you talking about a set of apples or a set of pen and apple, or just a set of things?
Just a set of things. We're mixing up. So the objects in the same set do not have to be of the same kind necessarily.
Okay. All right. Okay. Sure.
Yeah. Thank you, Charles.
Okay. Thank you.
So this is the closed interval 0, 1. Of course, I'm sure everybody here knows what it is. So it's a set of all numbers that are bigger or equal to 0 and less or equal to 1. And we can easily create out of it, a rectangular piece of paper like this, just by taking the Cartesian product of 0, 1 and 0, 1. So this will be ordered pairs, x, y, where...
You mean the cross, the fast equality?
Yes. Sorry, I made a mistake there. So this will be such a set of ordered pairs. And of course, by thinking of every ordered pair as a point on the Cartesian plane, then those points whose coordinates are limited by 0, 1 will exactly give me a square piece like this.
Right.
But now, let's say I want to make a cylinder out of something like this. So I want this shape. I could, of course, describe a cylinder as a subset of R cube, right? So we could really think of this as a subset of R cube. But then I have to worry about parametric representation of my cylinder. If my geometric shape is complex enough, then this parametric representation approach is going to be
quite complicated.
It's going to create a lot of bring in a lot of unnecessary technicalities into our discussion. So is there a simpler way to build, let's say, a cylinder out of a square? And at this stage, I'm not worrying about the structure of topology, which both spaces should have, and the construction I'm describing here could actually transform into a construction of the topology of cylinder seen as a topological space. We're just looking at the set theoretic part of the construction, not going into topology for now. So the way to build a cylinder out of a piece of paper, of course, we know how to do that. We just take the piece of paper, we do this to the piece of paper, we bring these ends together, right? So the square piece, maybe we want to stretch it a little bit, but the square piece is brought like this. I hope my picture is illustrative enough. And then eventually I want to stick these ends together. So eventually I want to do this. And so now the question is how to do that set theoretically once again. So set theoretically, this set is actually, this object is actually the same object as Cartesian product, because set theory does not know that you bended the sheet. But perhaps the same cannot be said about this set, where the point, let's say on this edge, and the point, the yellow point there and the orange point there, they've now been stuck together to be just one point, a single point, instead of two separate points.
So maybe at this stage, Zurab, we pause 1 minute and ask for help from our participants how to make this partition of this unit square such that we can get such a cylinder.
That's a good idea. So the question is, can we use the notion of a partition to create, to imitate this real-life construction that we want to glue basically these two endpoints of a sheet of paper to get a cylinder out of a square?
Any suggestions?
So either our question is too hard or too difficult. I mean, sorry, the opposite, too hard or too simple, right?
Too simple, yes, yes. So the question is, how should we do this partition of this unit square such that we get this kind of gluing and eventually we get this cylinder?
So I think Shimon wants to give us input on that. If it's
Yes,
all right, Francesco, to allow Shimon to speak as well. Thank you.
Sorry, I was noticed. He's on the way.
Yeah.
Are they? Can you hear
Hello,
Yes,
we
Shimon,
hear
we
you.
Thanks. So you can identify the points 0y and 1y for every y from 0 to 1.
Right.
Is
So
that,
each point on this side of the sheet, so which will have, of course, coordinate 0 and some y, we will group it together with the point 1y, right? And that we will do throughout. So for each y, such grouping will take place. And for a different y, there will be a different grouping. 0 y at 2, let's say, will be grouped with 1 y2. And this will happen throughout. So eventually, the effect of this basically is on this picture on the left side, I'm doing the groupings according to the points that are being connected by the yellow lines, exactly as if I was trying to glue them. But in a partition of a set, we need to make sure that everything falls in one of the groups. We cannot leave anything outside of the group, and that's not actually a problem, because
we identify the points in the interior of the square and on the top and bottom sides with itself.
yes, that's right.
Yeah.
So those points which are not on this on the edge, the way shown here, if I have some random point x, y, where x is strictly bigger than 0 and strictly less than 1, then the group will contain just that element and nothing else. So it's a situation where some groups, like on this picture I'm showing now, some groups only have one element in them. Some of them have 2, right? But some have 1. And these are the only kinds of groupings that we get for this partition. And with this example, I hope it's obvious that every time you want to kind of perform some kind of manipulation with your sheet of paper or maybe a rubber, and you want to create some shape by sticking some parts of your geometric figure with each other, you can use partitions to achieve the result. And another nice example is to fold the. So if we have a strip of paper that is not necessarily square, and we do what we just did with to get a cylinder, we get a band like this. But we might want to group things in a slightly different way, namely
we can twist it.
Yes, the group this one with that, group that with that. No, sorry, with that, and so on, and that with that, and so on. So the effect of this is basically that you take your strip, and then you twist this end, and then you stick with the other end.
End of it, yes.
And what we get as a result is, of course, the thing that's called Mobius Bandwidth. And one can get a Klein bottle with this construction and so on. So yes?
On this cylinder, maybe we just elaborate the fact that every individual point will be in one individual bag, whereas those who are on the sides of this left and right, they will be in one bag, in some sense. And that gives us this cylinder structure.
So as we see, there are multiple applications of this very simple idea of a partition of a set, and they also have an alternative description in terms of so-called equivalence relations. So maybe it's worth discussing what that is. So once I decide what things to group together, then those things that do belong to the same group, I could think of them as being related by a certain relation. For example, in this case, when we were creating natural numbers out of sets of objects, two sets of objects would fall in the same group if they had the same amount of contents in them, and that this defines a relation between objects in the group. So mathematically, on a set X, we can define a relation to be a subset of the Cartesian product. So the set of all ordered pairs that are supposed to be related. So just an example of this would be the set of all ordered pairs XY, such that let's say all ordered pairs of natural numbers, such that X is less or equal to Y. So of course this set of ordered pairs is not a function, right? But we can actually think of this set as the set theoretic interpretation of the less or equal relation. In a similar way, we could, because it encodes the full information about the relation, right? So given two numbers, 3 and 5, to decide that 3 is less or equal to 5, I just need to check that the ordered pair 3, 5 belongs to the relation R, belongs to the set R.
Same set, yeah.
Now, this is a mathematical way of, set theoretic way of describing relationships between objects. So seeing it as a set of actual ordered pairs that are related, where the first component is related to the second one. And just as another example, I want to give this this one, x, y, such that x squared plus y squared equals 1. So of course this is a relation whose graph is a circle, and a circle again is not a function, and we can think of this as once again a relation. So it relates two numbers x and y when their squares add up to 1. Anyhow, so that's the general notion of a relation on a set. It's simply a subset of the Cartesian product of that set with itself. Now, a partition on a set gives rise to a relation in the following way. XY belong to the relation, the order pair XY belongs to the relation. When X and Y have been grouped
by some law
in the same group. So there is some rule, as you say, that allowed us to do these groupings, and now we think of this relation of being in the same group, basically. So this is relation between X and Y that says that X and Y are in the same group.
Then we can ask, what kind of property should it satisfy?
And then it turns out that this, so it turns out that this relation has 3 very important properties. One is that for every X in the set, so this is just a symbol for every, so this just means for every X that's an element of X, we have that the X is related with itself. So in other words, of course, everything will belong to the same group as itself. This is obvious, huh? And this property is called reflexivity. Then another property is that if we have 2 things and X and Y are in the same group, then also Y and X should be in the same group. And that's also quite obvious, right? If X and Y belong in the same group, then it doesn't matter in which order we describe that they did belong to the same group. The order of X and Y doesn't matter. And the third, so this property is called symmetry. And the third property says that given 3 things, if X and Y belong to the same group and Y and Z belong to the same group, then X and Z must belong to the same group. And again, this is quite obvious, right? If X and Y do belong to the same group, and Y and Z belong to the same group, then X and Z must belong to the same group. And by the way, this is this illustration of the idea that you cannot have groups that overlap. You cannot have that situation, as we already discussed. A situation like this would make X and Z not belong to the same group, even though X and Y and Z do. So this property is called transitivity. And then it turns out that these 3 properties are enough to describe partitions. And what I just said can be once again turned into a very precise theorem, a very simple but precise theorem in set theory. Even though I say simple, but for the first time, this theorem, when the students encounter undergraduate courses, it takes a while for them to wrap their head around it. So the theorem says that there is a 1-to-1 correspondence between the set of all
partitions
on a set X and the set of all relations satisfying these 3 properties. That's right, but and such relations have a special name. They're called equivalence relations.
Equivalence relation.
So there is a precise matching of partitions and such subsets of the Cartesian product. And the reason why they're called equivalence relations, of course, is that basically by grouping things together, intuitively, we can think of this as a way of not distinguishing between the members of the group. Just like Shimon was telling us that when he was describing the partition, he was using the terminology that you identify something with something else. So you identify one, let's say this with that. Identify means you're not distinguish between them.
Distinguish between these two.
So
yes.
in other words, you think of them as being equivalent. You think of these things in the same group as being equivalent to each other in a certain sense. And so this is the precise notion of equivalence relation. And it is another way of describing a partition. And then in some nice situations, like for groups, it turns out that equivalence relations that after partitioning your group, you still get a group with the previous operations, that information becomes encoded by the grouping of the zero element of the group if it's additive group. And so groupings of zero elements are called normal subgroups. And we have similar story with rings where normal subgroups are replaced with ideals. And so this goes into a lot of abstract structures that are needed not just in mathematics, but also outside mathematics. And the construction is called quotient structure. So when this thing itself is a mathematical structure, let me actually go back to the original picture. When X is a mathematical structure, so it's not just a set, it has some further structure on the set. Like, for example, it could have topology on the set. When we consider the partition in such a way that the partition, the set, inherits the structure of X, then this P is usually called the quotient structure of X.
So maybe we should give a concrete example, another one from integers to show that we can get a new structure. Say, for example, if we make, say, multiple of another number from integers.
Yeah, okay. So a good example of what we were just talking about is if we take, let's say, the integers and think of it in terms of its structure of, let's say, addition. And let's group integers in the following way. So let's first write all the integers out, 0, 1, 2, 3, 4, and so on. And maybe I'm going to write them out in a slightly different way. So let me write in multiples of 5. So 0, minus 5, minus 5 goes on the other side.
Yeah.
Minus 5, 5, 10, minus 10, and so on. And then 1, 6, minus 4, 11, minus 9, and so on. And then we have 2, 7, minus 3, minus 8, 12, and so on. And 3, 8, 13, minus 2, minus 7, and 4, 9, 14, and so on. Minus 1, minus 6, and so on. So this way I've listed all the integers. But the reason why I did it the way I did it is because to show the groupings. So we have 5 groupings here. And this new set that is created out of this, so these groupings themselves now they are elements of the new set. This new set is usually referred to as Z5. It's referred to Z5, and sometimes it's written out as a quotient of Z over 5Z. And what is nice about this is that it inherits the structure of addition in the way that we can add these groups themselves, and that could correspond to addition modulo 5. But to ensure that addition transfers to this partition, we need to make sure that, let's say, when I add minus 5 with 1, right? So what is minus 5 plus 1? Minus 5 plus 1 is minus 4, right?
Mm-hmm.
Maybe I want to make a different example to make it more illustrative. Let's add 1 and minus 3. 1 plus minus 3 is minus 2. So the sum of 1 and minus 3 is minus 2. So I could think of, then this group plus that group. So in other words, this element and that element, their sum being this element right here. But I have to be careful, because what if I had picked different representatives? Maybe their sum would fall in a different group, so that the answer would be different for the sum of those elements. So the sum should not depend on choosing the representative, otherwise the operation will not be well defined. But of course, it turns out so that it's not the case. If you add 7 and 11, you will get 18, and 18 will be in the same group. In fact, it would have been the next number here, since I'm actually writing these numbers in such a way that every next one is 5 plus the previous one. So if I pick different representatives from the same group, I would still get the same group as a result. So the resulting group is independent of which representatives we add. And this is what allows us to define addition on this partition. And so that is what usually one means by the group Z5. Which in a sense is addition modulo 5, because what we are counting here is of course the remainder. So this is when the remainder is 0, when the remainder is 1, when remainder is 2, remainder is 3, and remainder is 4.
So it could be a good exercise, very simple although, but to show that the same construction we can also get by defining a good relation, which will eventually become an equivalence relation. Because we just mentioned in that theorem that this idea of partition is essentially the same thing as getting an equivalence relation on our side.
Yes, and in a situation like this, when our equivalence relation was chosen in such a way, or partition was chosen in such a way that it matches, that the operation behaves well with it. The operation is kind of compatible with the operation, because the result of the operation does not depend on representatives of the groupings. Such equivalence relation is then called is said to be a congruence on your mathematical structure. But now it takes one to a completely separate course, perhaps even. So the idea was just for those who maybe have encountered these ideas to connect it with the theme of the present lecture of partitions, and to show how in many different ways the partitions can be used and how central they are in terms of encoding formal ideas in the language of set theory.
Yep. So what we did today, Zurab, maybe we summarize the whole thing.
That's a good idea. So we looked at the concept of a partition. We looked at applications of partitions. And we looked at
the concept of equivalence
describing
relation.
Yes, describing partitions in terms of equivalence relations.
And in some sense, conversely, because we gave this 1-1 correspondence in that theorem.
Yes. Yeah, that's what I mean describing. So they give full description. Equivalence relations give full description of partitions.
Good. So maybe in last 4 minutes we wait for ask our participants if they have any questions or suggestions or remarks. What do you think?
That's a good idea.
I cannot see any raised hands at the moment. Yeah.
Someone needed this subtitle
Here we go.
facility.
Charles.
Yeah.
Charles.
Yes,
ready.
Charles.
Charles, you are online.
I wanted to go a bit back to the pairing of integers.
Right?
Yeah, you see where you've got 1 + 1 different from 2 + 2.
Yes.
You mean 1/1 different from 2/2?
No. As a pair.
Right. Okay.
As a pair. I thought maybe wasn't it maybe before we say we do that comparison, just define equality of a pair in the way you later did with n times L minus mk. To say that pair is equal.
So pairs are defined as sets, and that comes from, I think, already from the first lecture.
Yeah, in the first lecture, we explained when two pairs are same.
Pairs are defined like this, Charles.
Yeah.
And if you have two pairs, so the consequence of this definition is that if you have two pairs,
yeah,
the only way they are equal is if their components are equal.
Equal, yeah. So that's what I wanted to that's what I'm thinking about, that instead of in this context in particular, wasn't it necessary to define a new kind of equality, which is different from that one? Because that
That's exactly the equivalence. Yeah.
Yeah. That one.
That's exactly the equivalence relation.
That's which is in this blue rectangle.
Yeah. So I'm saying that that's what I'm saying, that instead of emphasizing that inequality there, wouldn't it have been better to, before we talk of equality there, define what means equality in this context?
So what you're suggesting is an approach to this topic where we first begin with the idea of equivalence relation, so which we can think of as generalized equality. We first begin with this idea, and then we create the notion of partition out of it. But the approach we took for this lecture was the other way around. We started with the idea of partition and then extracted the idea of generalized equality or equivalence relation from it.
Okay.
But maybe it was worth mentioning that in this example, this equivalence relation will be the idea of
equality.
Fractions being same.
Equality, yes.
Yeah.
Equality itself gives an equivalence relation, of course.
Yeah. Okay. Yeah, that's what I just wanted to make a comment on. Yeah. Yes.
Thank you, Charles.
Sure. Thank you, Charles.
Sure.
I think there is a question by Lebogan. Please, you just need to unmute yourself and you can ask the question. Hello?
We cannot hear you yet.
No.
I think your microphone is muted, so you need to unmute your microphone.
There is also, maybe while we're waiting for this,
there's a Q&A, yes. Bibliography.
Yes, I would want to be a bit more prepared to answer this question, because definitely the internet is full of resources on set theory, but maybe not all of them, maybe most of them are not accessible enough for someone who wants to begin mathematics with set theory. And then the link that is usually posted for these lectures on YouTube, there is a link to my webpage where I post these notes as well, these notes. And there I will be adding some references to the bibliography. So you will be able to find it there.
Thank you, Zurab, for that. And I wanted to quickly make a comment. One of the participants asked me to switch on the subtitles, which is a really fair request. But I fear one needs to do it before the meeting starts, because at the moment I don't have any option to change anything. I will try to do it for the next time.
Thank you.
Thank you.
unless there is something in Zoom that I have no idea how it works, but I can't find any options at the moment. I will Google around and make sure that we have it next time.
Thank you, Francesco.
No, thank you. Okay, it looks like there are no more questions or raised hands from the participants. Then Zurab and Amartya. Charles. Charles is back. Charles, please go ahead.
Charles, microphone.
I can unmute Charles.
Right. Yeah, I'm unmuted now.
Yeah.
Okay. Yeah, exactly on that this display which you're having. Yeah, maybe don't move it. I just want to make a comment on. I'm now talking in terms of the school context, in terms of integers, coming to integers. You've taken away the slide which I wanted to refer to. The ones for, yeah, this one. Maybe you can write there 2 plus, what's this? 2 plus 5 equals to 3.
Equals to 3.
Yeah, no, sorry. I want to say, no, I don't want to say that. I want to say 2 plus x. Let's see, just a second. Equals to 1. Equals to 1. Yeah, it's just a suggestion which I'm asking maybe to think about it also. I'm talking in the context of a school, like maybe trying to introduce integers in a kind of, I don't know which I could describe it as a constructive way, in such a way that when you do that arithmetic within the whole numbers and the natural numbers, you get x is equal to -1. And then somewhere there you problematize that we actually, it's a kind of a situation. I mean, if you take a school child whereby it takes a subtraction as some kind of taking away from a certain side, then you can take 2 from 1. Then you problematize it in such a way that is something which we don't have kind of, like we don't have enough numbers to create answer to this one. And then from there, motivate the construction of integers. But instead of approaching it this way, another approach, you then try to look at natural numbers as classes of differences, like 1 would be 3 minus 2, 5 minus 4. Then you maybe use also the number line there, which is very popular in school. Then you put these bags of differences going in the positive direction. And then by that time, obviously, it will make sense for a child to say 1 minus 1, if there's nothing, then maybe there you are sensitizing the kind of a 0. Then also if there's a 0, then you notice that all these differences you put there, they are equally spaced together. So this one of 0 will be a difference which is basically before 1. Then from there, you now kind of mirror, like geometrical, basically, kind of geometrical, you mirror, put the mirror line on 0, then you'll see that what was 3 minus 1 becomes 2 minus 1. What was 2 minus 1 becomes 1 minus 2 on the other side of the mirror. Then from there, geometrically, you create these bags of things going to the negative side. Then you kind of, again, there you've got kind of these equivalent classes of differences. Then you name them like that. Then you end up naming them the ones on the left as one on the left, 2 on the left, and that. Then that way you've extended the whole numbers and natural numbers. By whole numbers, this case, in the way I'm talking natural numbers without 0, then whole numbers, natural numbers with 0. Then you get that kind of a thing. Then after that, you introduce the arithmetic of those numbers.
Yes, thank you. Yes, of course. So it's a general phenomenon that there are multiple ways of defining the same idea. I think what we did here is closest to your idea of mirror, putting a mirror. because we basically, this is the place where the mirror has been placed, so that does not get reflected itself. And we duplicated the non-zero numbers, and that's basically one of them is the actual one, the other one is the mirror reflection. So it is of course nice to motivate these kinds of constructions in such a way, and in set theory one does end up trying to prioritize those constructions which are closest to the real life intuition. So thank you for that remark. It is actually important to be close to real life intuition, because then you make mathematics easier and more understandable, more intuitive in a way.
Yeah, I think that was my comment just for just commenting in relation to actually the school context without maybe very powerful set theory.
Of course, there are a lot of intuition, of course, is very important, and in some sense the task of set theory is to answer the following question: can everything that intuitively makes sense and is intuitively logical, can every such thing be actually turned into an actual logical thing to the point that we could teach the computer to do the logic for us? And the answer is yes, thanks to set theory. And we're now learning those tools of set theory which enable to turn any kind of intuition into a very precise formal computational material.
Okay.
Excellent. Then I think if there are no more questions and useful comments, thank you very much, Charles, for those. I will thank Zurab and Amartya, and it looks like Amartya is ready to leave us. So thank you very much, Zurab, for another great lecture on set theory.